Hi, everyone. It's 12:01, so we'll get started. Hi, this is Jason Key at SP Grid at Harvard Medical School in Boston. Thanks for signing on today. Today, I'm happy to say we have Stephen Ludtke from the Baylor College of Medicine. Steve's focus is on single particle reconstruction from cryo-electron microscopy data. So Steve is the developer of EMAN. So today he'll be telling us about EMAN2. So Steve, go ahead.
Okay, thanks a lot. Let me give at least a little brief introduction as to what single particle reconstruction is, since I don't really know who the audience is here. Basic idea is we take electron micrographs of purified macromolecules in an aqueous solution, which have been vitrified, which is frozen very rapidly on a thin electron microscope grid, and then we image those molecules and basically in a time snapshot of their solution configuration. So what we're seeing here is a sort of a typical micrograph of a molecule called MMCPN floating around in random orientation in solution. So each one of these little black blobs in here is the image of a molecule, macromolecular assembly floating around in solution. So the idea then is we take a bunch of these images and we select all of the individual particles that are present in the images into a big population. So this, what I'm showing you here is a population of about 432 out of the 30,000 particle data set that was used then to produce a three-dimensional reconstruction. So we take these particle images and we go through a processing loop, which I'm not going to get into great depth today, just in the interest of time. But the basic idea is we start out with particles, and then via an iterative process, we eventually wind up with a final reconstruction. So from those 30,000 particles, we can get something that looks sort of like this. So for many years in the cryo-EM field, the first 3 decades or so of its existence, it was famous for producing structures like this, the so-called blobograms, which is low-resolution structures which were high enough resolution to see some of the quaternary features of the molecule of interest, and you could maybe dock a crystal structure into it, but you couldn't really directly interpret it in atomistic fashion. Over the last 3 or 4 years, we've seen the emergence now, though, of structures where we can actually see side chains, very much like X-ray crystallography. So the resolutions are now in the sort of the 3 angstrom ballpark, and compared to crystallography, cryo-EM actually tends to have better phase information, which means that at an equivalent resolution, you can often actually see a little bit more in cryo-EM maps than you can in crystallographic maps. So this turnaround is primarily due to development of new detector technology, which collects better quality data from similar sort of images. Now, the images I showed you a second ago were pretty noisy, and of course, the noise in this case is due to the fact that we have dose limitations. As we're irradiating the specimen with the electron beam, we're gradually destroying the protein molecules that we're trying to image. So we're limited in how long an exposure we can take on the specimen. So if we develop a better detector which can collect more information for a given amount of exposure, we can get more information out in the end. And these new detectors have allowed us to sort of surpass the threshold from sort of the sub-nanometer resolution. This isn't even sub-nanometer. This is about 11 angstroms. The sub-nanometer resolution where you can begin to see secondary structure, now all the way down to the point where we can begin to see protein side chains. If we look, though, at the distribution of published maps over the last few years, we'll see that despite the new technology, still only about 10% of the structures are at the sort of better than 7 angstrom resolution regime in which you can probably at least trace the protein backbone in your structure. The other 90% are still at considerably lower resolutions. And I'll point out that most of the structures at this very low resolution extreme, this 25%, is actually using a related technique involving subtomogram averaging in cryo-EM. Not all of them, but most of them. But still, about 2/3 at least of the structures being produced are fairly low resolution still. Now, the question might be whether that impacts the importance of the publications. So if we take a look at the number of Nature, Science, and Cell papers published as a function of resolution in cryo-EM since 2010, since we've been getting these high-resolution reconstructions, we can see that actually even if you have a lower resolution reconstruction, you may still be able to answer some high impact biological problems. So while it's terrific if we can get high resolution in every case, the practical reality is that you're not going to get to high resolution in every single structure, but that doesn't mean you can't answer good questions. Now, the reason you can't always get to high resolution is one of the main reasons is, in fact, that the molecules that you're looking at are often moving in solution. Now, the images we're collecting in the microscope aren't actually moving in that way because the molecules are frozen in ice, but what we'll see is a population of particles in a variety of different conformational states. So for example, over here we see fatty acid synthase, which is undergoing about 30 angstroms of motion in solution. So if you want to take that, if you wanted to take this structure and produce a set of, say, 3 angstrom resolution structures, that means given the three dimensions, the multiple degrees of freedom that we're dealing with here, we would have to create literally hundreds of different structures, and we would have to have tens of millions of particle images to get enough statistical information that we can actually get to very high resolution. So the typical reconstruction of a map like this is going to be limited in resolution, even if you deal with the dynamics somewhat to probably the 12 to 15 angstrom regime. But other structures will be much more rigid in solution, and in those cases it won't be as much of a problem. Now, if we look over at the software community for CryoEM, there's actually quite a few software packages available in the field, and even this isn't all of them. These are just the ones that have produced at least, I think, 5 structures over the last few years. And we'll see that for many years, Spider, Magic, and EMAN were sort of competing with each other for dominance in the field. Over the last few years, we've seen the emergence of another package called Relion, which was produced out of the MRC in Cambridge. And this is predominantly because it was used for a number of very high-profile, high-resolution structures. Some of the first structures coming out of these new detectors were refined with Relion. People say, oh, wow, beautiful high-resolution structures. I need to use that software. Now, Relion is an excellent piece of software. I'm not saying anything bad about Relion. I will point out, however, that if you take pretty much any of the popular CryoEM software packages and put really good data into it, you can get out virtually identical maps. So this is this exact same data set. This was a data set that was actually first published with Relion as a demonstration. So it's a publicly available data set. We processed the same data through EMAN, the same data through Relion, and here are resolution curves. You can see that they match almost perfectly, and the structures are virtually identical. You'll see some subtle differences in certain locations, and that's actually an important point. The other point that since I'm advertising EMAN, that I'll point out, though, is that the amount of CPU time required to achieve the structures is considerably different. In a typical project, it's typically about an order of magnitude more compute time required for Relion because it's doing maximum likelihood integration, whereas EMAN is using more optimized techniques. Why might we actually want to use multiple software packages? Here, what we basically found out is that we have pretty good data and that there isn't much difference in interpretation. If we look at this structure and we interpret what's going on biologically, and this structure and interpret what's going on biologically, our answers aren't really going to change. If we look at data sets that are undergoing some amount of dynamics, the sort of thing that I was showing you here, some sort of molecular motion, then we'll actually see that the different software packages deal with that flexibility in different ways. So these are 4 different structures of IP3 receptor done with 4 different software packages. And you can see while they agree overall into shape, as the conformation of the particle, if we look carefully at specific domains, we'll see that there are some significant differences. We'll find differences in orientation in certain domains in the particles. We'll see difference in level of detail, that sort of thing. So it can actually be a valuable thing to take your map and reconstruct it in a couple of different software packages anyway, and just convince yourself that you're getting the same answer. If you're not getting the same answer, to make sure that you're very careful when you're interpreting the regions where you see differences. All right, so that's my general introduction to CryoEM in 10 minutes. now let me give you a little bit of background into Eman, and I'll do that for probably 15 or 20 minutes, and then I'll do some live demos, and we'll take a look at how the software can be used. So here's the basic information for Eman. There's a nice wiki page which contains all of the documentation. The wiki is blocked for people subscribing to the page as editors due to spam problems. But if you send an email to us, we'll add you so you can actually edit the pages and contribute to the documentation effort. The software download is of course available through the wiki as well, but here's a direct link to the software download. And we also have a Google group, which is used for discussing as a mailing list, basically for discussing Eman-related issues. And I think there's a couple hundred subscribers to the Google group. So, things that are good about Eman. We have a complete graphical workflow interface, which I'll show you in a couple of minutes, which allows particularly novice users to go through the pipeline for single particle reconstruction or for subtomogram averaging. And it's honestly not just for novices. I actually use the workflow interface myself because I find it more convenient to go through the pipeline in a consistent way. So we have that's associated with the project system. So basically, a particular project, a particular refinement, will live within one folder, and there's a set of standard naming conventions that we use for all of the subfolders inside the folders and that sort of thing. So the data is all organized in a fairly self-consistent fashion, which means if you ever need to go back and look for some particular bit of information as you're publishing, writing up a paper for your results, it's always easy to find. We use a combination of Qt and OpenGL for all of our graphics in the interfaces. So in most cases, when you're working on a cluster, you're not going to be remotely running the graphical interface from the cluster. And I'll describe how we typically work with the clusters for doing our refinements and integrate that with your local desktop machine a little bit later in the demonstration and the presentation. This is just a benefit over people who might still be using Eman1. We have made some dramatic speed improvements in Eman2 over Eman1 through optimizations of various processes. So it's well worth switching for that reason. Something that's come out in the field recently is a stronger need for validation. So one aspect of this validation is using a so-called gold standard approach for determining resolutions of maps. It used to be back in the last decade that when structures were determined, the methods that were used to assess resolution varied pretty considerably from one software package to another, even though they produced curves which looked like they were directly comparable with one another. And that meant that resolution wasn't really a very robustly defined phenomena. So both Eman and RelyOn now use this gold standard method, and you can use the same method in other available software packages as well, even though it may not be quite as integrated. It's not a solution to all of the validation problems in the field, obviously, but it is a solution to at least a couple of problems in the field. We have a nice method for particle-based micrograph evaluation. One of the issues in the field is you get a micrograph. Typically you look at the power spectrum of the micrograph, which gives you some information about the resolution of the information that resides in the micrograph. However, the issue with the micrograph-based approach for evaluating the quality of the images is certain artifacts in the micrograph. For example, if you have a lot of strong scatterers in the buffer that you're using to hold your molecules, or if you have a continuous carbon film supporting your specimen, or other things like that, it can lead to apparently high information content in the image. If you look at the power spectrum of the image, you see a lot of high resolution signal, whereas it's actually most of that signal is actually noise. It's things like the carbon film, which aren't contributing towards the quality of your reconstruction. So we actually have a novel particle-based approach, which allows you to really assess whether your individual images are good or bad, and whether you should throw them out or keep them. We've established a scheme for interoperability with FreeAlign and RelyOn, and I'll talk about that a little bit more later. We support other methods than just single particle reconstruction. We have tilt validation, random conical tilt reconstruction. subtomogram averaging, and population dynamics, which produce those sorts of little pseudo motion movies that I showed you a couple of slides ago. We have support for basically all the documented CryoEM file formats, and you can use Eman as utility to interchange data between the different file formats and conventions. We've got over 200 general purpose image processing algorithms. And for those of you who might have played with EMAN2.0 and been frustrated by this database system that we use to store data and metadata in there, we've eliminated that in EMAN2.1. So now everything in EMAN2.1, metadata is stored in human readable flat files, and image data is all stored in HDF files, which are it's a broad multidisciplinary standard. So the overall architecture of EMAN2, standard sort of hierarchy. So at the base, we have a C++ core library, which performs all the high performance image processing operations. Then that's wrapped inside a Python wrapper, which allows us to organize higher level code in the routine in a more easily understood fashion. It allows us to do certain things much more easily than we can directly in C++. Then all of the command line programs within the system are written in Python, which then make use of the C++ library. These low-level command line programs are then used within higher-level programs, which do things like the full three-dimensional refinement process. And then that is in turn used by the project manager interface, which allows users to get a quick start into the system. This is just a list for those who are actually in the CryoEM field of the various file formats that we support. This isn't actually a completely exhaustive list. If you look in the wiki, you can find a complete list. But we basically support all of the commonly used file formats. We use a standard convention for all of the programs in EMAN2. We didn't do this in EMAN1. So all of the EMAN2 programs start with E2. That helps distinguish them from programs that might be produced. So we have a program called Refine, for example. Instead of being called Refine, which might conflict with other software packages, we call it E2 Refine. The only conflict you run with E2 is in Linux. There's an ext2 file system, and there are a couple of utilities which start with E2, but none of those are Python scripts, so there's no real conflict there. So if you look at any of the documentation, we use a pretty standard sort of naming convention. You have E2, then the name of the program .py. Anything in greater than, less than symbols is a required command, parameter, and anything in square brackets is an optional parameter. And we use very standard Unix notation for all of the options. There's a nice command called E2 help, which I'll talk about a little bit later, which gives you information on certain categories of algorithms that are available within the system. And I should add that if
All right.
Hello, hello, hello.
All right, we're good now. I can hear you
Okay,
now.
good.
I'm not sure what happened there, but go right ahead.
All right. I will. You've got my screen again too, right?
Yep.
Okay, good. All right. So not sure exactly where you lost me. I'll just start on this slide again. So even if you're primarily a user of some other software package, Eman offers a variety of utility functions which can be used to interconvert file formats, display images, plot data, that sort of thing. So these are sort of general purpose utilities you can use. E2 display is a GUI for general purpose image visualization that's compatible basically with every file format that Eman supports. Basically, any program in Eman will read any file format that the package supports, and in most cases, you can write to any file format as well, and it'll use the extension that you provide as a hint to what format you intend. E2 Proc 2D and Proc 3D are sort of general purpose 2D and 3D image processing programs. ImInfo will give you general information about images, what format it's in, what header values are, that sort of thing. And then for more advanced users, there's a Python interface which gives you access to all of the Eman libraries from at a Python level. There's a bunch of different graphical tools. The project manager is sort of the primary one that most people will use. Most of the other utilities can be launched from the project manager, including E2 Display, which is the general image viewing program. So I'm not going to go through these in any length right now, although I'll show you a couple of them later on in the demo. Then there's some higher level programs. These are the programs which do things like 2D reference-free class averaging. E2 Refine Easy is the program that produces a 3D structure from 2D particle data. Initial model comes up with sort of an initial guess at a three-dimensional structure based on your two-dimensional class averages that you produce here. So there's a variety of these high-level programs which perform different tasks within the system. And if you want any details on any of this stuff, we have a number of very nice tutorials available on the website which can take you through the entire system. We have a nice tutorial which will get you to a sub-nanometer resolution reconstruction from a set of sample data that we provide. Basically, you can do it in an afternoon on a laptop. As I mentioned before, we've added some intercompatibility between Eman and some other packages. So it's now possible to take, if you've done a refinement and rely on, you can run one program. It'll take all the rely on information, convert it into an EMAN2 project, and then you can run an Eman refinement as a comparative study. Or vice versa, once you've done a refinement in Eman, you can generate a rely on refinement directly from that. Similarly, for FreeAlign, you can export data in FreeAlign format. It handles all the data format conversions, all the metadata conversions, everything, so you can get started immediately. There's also an emerging standardization effort in the CryoEM community called EMX for EM exchange format. And this is endeavoring to have a standard format for metadata exchange among software packages. It's still in sort of its fledgling state at this point, but we're fully supporting and committed to that effort as well. So these are the commands that are actually used to perform the interoperability, although again, many of those are available through the graphical interface. Eman uses a modular infrastructure in the C++ library. So if, for example, someone adds a new image processing algorithm or they add a new 3D reconstruction algorithm, that sort of thing, they can add it directly to the system and it immediately becomes available to all the programs in the system by name. I'll show you a little bit of how that works later on, at least with reference to the general image processing algorithms. I think that number is probably over 200 now, but anyway. So it's a nice modular infrastructure, and if you are at the level of developing your own C++ code and you want to have an integrated system where you can just test some new algorithm, we make it very easy to add new algorithms to the entire system. Okay, let's just talk a little bit about refinement and about how this fits in with the concept of using supercomputers. So I've broken down the process of going from these 2D micrographs you collect on the microscope all the way through a three-dimensional structure. Now, I have to point out there are other methods that you can also use in the field. For example, if you do helical processing or 2D crystallographic processing, those methods are going to have different values in all of this. I'm really just talking about single particle reconstruction here. But as single particle reconstruction is sort of the dominant force in the field at this point in time, it covers sort of the vast majority of cases. Now, one of the issues that people have run into with these new detectors is they collect data tremendously faster than data used to be collected. So it used to be you'd have a 1 second exposure on the microscope, and that would give you one micrograph. And the micrograph would be, say, 4K by 4K pixels. The new detectors, not only do they have a better quantum efficiency, better signal-to-noise ratio, they can also collect data in the so-called movie mode, which allows you to compensate for the slow drifting motion that you may get from the stage or from the specimen, or when the beam impacts the specimen, it may cause things to move around a little bit. So instead of collecting an individual frame in a 1 second exposure, you're collecting, say, 30 frames in a 1 second exposure. What that means is on a current generation microscope, in one day, you can typically collect about 4 terabytes of raw data. Now that 4 terabytes of data, say we're using about a day and a half worth of data here in our project, so that 6 terabytes of data will eventually process down to about 150 gigabytes. So there's a tremendous reduction in data here. And this pre-processing task, going from 6 terabytes to 150 gigabytes, the primary computational requirement here is actually for data bandwidth. Very often you'll go to like a center and you collect all of this data and it'll get stored on external hard drives. You then have to read 6 terabytes of data from an external hard drive, and you can only usually do that at most about 100 megabytes a second. So the limiting factor isn't the computational power that's involved in reducing this data back down to its final size. It's actually the speed at which you can read the data off the hard drive. So there's very little point in trying to go to a cluster for any part of this process, because the drive will read the data as fast as it reads it. It's not gonna speed up anything. Now, some sites you'll find they actually have a dedicated 10 gigabit data line from the microscope to another computer where they can do the pre-processing, and then they'll just give you the 150 gigabytes when you go back home. But still, people very often want the raw data because they say, well, maybe they'll come up with better algorithms for processing, that sort of thing. All right, once you got the 150 gigabytes, you then go through the particle selection process. You isolate the individual particles from each of the micrographs. And that'll typically take you down from, say, 150 gigabytes of data down to about 20 gigabytes of data. Although it varies with the density of the particles, and the amount of processing time and human time involved in this process also varies a lot with the methods that you use when you do this. The next step is CTF correction. This actually produces an increase in data size again because you derive corrected particles from the original particle data, and you don't delete the original particles. So you actually sort of increase the size of data. But this doesn't actually require a whole lot of CPU time in general anyway. You'll find that some of the workflows people use for doing this do involve running a little bit on a cluster. But in a lot of workflows, you're really only talking about 1 CPU hour of total time for this volume of data. If you use some other algorithms, maybe it's 10 or 20 CPU hours. It's not a tremendous amount of computation. All right, so once we've gone through this processing, the next step in an EMAN workflow is to generate 2D class averages from the data. And again, this really doesn't use a tremendous amount of CPU time. So in most cases, I just recommend people do this on a desktop machine, workstation, whatever. If you have a workstation used to do the pre-processing, it's generally going to be more than powerful enough to do this. And usually, you'll have, say, 8 cores on the machine, so you finish it in an hour or something. It's not worth the effort to get it to a cluster. Then taking that and producing an initial 3-dimensional structure, again, it's not a very long process. 10 CPU hours actually may be more. I mean, you may only need 1 or 2 CPU hours for that processing. So really, the only step in this whole workflow where it's really necessary to move to a cluster is the final refinement process. And you can see I have quite a range here, 3 orders of magnitude, anywhere from 10 CPU hours to 10,000 CPU hours. So again, some of this scaling, if you're talking about 10 CPU hours, it's a smaller scale project than this. But realistically, the scaling of the number of particles, the amount of data you need, and the amount of CPU time you need scales very, very poorly, typically about the 4th power with the resolution that you're trying to achieve, or inversely with the 4th power of the resolution you're trying to achieve. So if you're trying to get, say, a 20 angstrom resolution reconstruction right now, and with current computers, you can do it in a laptop in a couple of hours. You don't need a cluster. If your goal is to get to 2.8 angstrom resolution, you may end up using 50,000 CPU hours on a fairly substantial cluster. So the range of computing that's required for different scale projects varies tremendously from one project to another. All right, so here's the typical strategy that we use with doing refinements using EMAN in a cluster environment. So you'll have EMAN2.1, hopefully the same version. Doesn't have to be exactly the same, but it's not a bad idea if it is. Installed on both a local workstation and a cluster. Then we recommend that people do all of that initial pre-processing and processing on the workstation and not bother going to the cluster. Then once you've got it to the point where you're ready to do a big job, you then rsync the project to some folder on the cluster. So just copy the entire project folder directly to the cluster. Not only does this make sure that you've got all the files that you need when you're doing your refinements there, it also gives you a backup of your data. Now, if you have an environment where you have a shared file system where the cluster can see the same file system as your workstation, well, of course, that's fine as well. It's perfectly safe for that sort of computing for almost all operations. It's probably not a terrific idea to try and write to the same HDF file at the same time from two different computers on a shared file system. But other than that one caveat, there shouldn't be any problems with it. Then once you got your data, your project folder on the cluster, then you run this refinement task on the cluster using standard cluster techniques. So we support OpenPBS, SGE as batch queuing systems. If you have some specialized batch queuing system, which we don't directly support, there's a shell variable you can use which allows you to specify MPI options and deal with that situation. The way E2Refine Easy works is it will call MPI run multiple times as it goes through its processing. There are some tasks that it performs only using threads on the local processor. There are other tasks that it performs using MPI on the entire cluster. The majority of the time is spent using MPI, but there are a few tasks which just don't parallelize all that well. And it'll just run on the first allocated node that you get. So you don't run E2Refine Easy directly with MPI run. You launch MPI run and you give it you launch E2Refine Easy and you give it options telling it about how the MPI environment that it's going to be running in. Then it will run jobs as necessary for as long as the job continues. Then while the job is running or after the job finishes, you can just rsync-avr your project back from the cluster to your local node, or if you have a shared file system, you can just access it directly. And then you can visualize what's going on and look at the results back on your local workstation. While you can find environments where they've set up remote OpenGL visualization stuff directly from the cluster, I've found that those situations are unusual rather than the standard environment. So, and generally speaking, you'll get much better performance, et cetera, if you just do stuff on your local workstation. Since we use OpenGL for all the graphics, getting it to work across the network connection is always a little bit of a pain. So this is sort of our general strategy. Since we're using rsync, it only copies files that have changed during the refinement procedure, both going from the cluster and back to the cluster again. So you can basically keep your folders in sync back and forth. And again, that way you have a backup and you know what's going on. So that's the typical way you go through a project. Okay, so I'll take the rest of the time and just give you some demonstrations of how Eman works and how you might use it to synchronize things with a cluster. I could probably do this for 3 or 4 hours if I wanted to. I'll try to limit myself so we finish at the end of the hour, basically. And again, if anyone has any questions, feel free to just sort of butt in and speak. I can take a look here and see if I don't see any messages in the group chat. So I'll just proceed with this. So what I've got here is I've copied a particular project directly onto my laptop. This is just a standard MacBook Pro. So this is what a typical refinement directory will look like. there are standard naming conventions for all of the different folders that you'll find here. And if you look at the wiki, so here's the main EMAN2 wiki, one of the things that you'll see here is a page that has standard folder descriptions, and it'll tell you what the names of all these subfolders are and what all the files in the various folders are. Just sort of briefly, there's some obvious ones like micrographs, that contains the raw averaged micrographs, movie, which would contain the movie data that hasn't been aligned and averaged yet. Particles contains the particles once they've been boxed out. This also contains various versions of the particles once they've been corrected for the contrast transfer function, that sort of thing. And then we'll see these various numbered directories. So R2D stands for refine 2D. So this is the output from generating 2D reference-free class averages. And then when you run 3D refinements, it produces these refine directories. Every time you run a new 3D refinement, it makes a new numbered directory for you. And then you can sort of progress and follow through the entire history of your project. Right, so I will launch the project manager here, and we can take a look at how things work. Now, on a Mac, it doesn't always bring the window up to the front for you. I thought, yeah, okay, it actually did eventually bring it up to the front here. On certain versions of EMAN2, you may find that it doesn't bring the window to the front directly. All right, so here's the project manager. The font is probably going to be a little bit small, so I'll sort of read off what it is I'm looking at here and explain what we're looking at. So what we're seeing over here is the standard workflow, the sequence of events that you would typically go through for a single particle reconstruction, starting with raw data, then particles, contrast transfer function, sets of particles, reference-free class averages, making an initial model, then running a 3D refinement. Now, if you've started in some other software package and say you've boxed out all your particles, you can merge into this process at any point in time. You don't have to go all the way back to the raw data. But if you do go back to the raw data, then there are tools available. Each of these is an expandable list. For example, evaluate and import micrographs. This will let you do initial evaluation of the quality of your images before you decide whether you want to process them any further in the project. Then once you get down to particles, there's access to Eman's particle picking methods. There's mechanisms for importing particle location information from other software packages, that sort of thing. Then once the particles have been extracted, we get down to contrast transfer function, and then there's a series of steps that you go through, and the tutorial explains all of these for looking at the contrast transfer function of your data, assessing whether the individual micrographs contain good data or bad data, maybe importing CTF information from other software like CTFind3, which is popular to use in the community, et cetera, et cetera. And if you've done something like that, if you import with CTFind3, that doesn't prevent you from using Eman's particle-based micrograph assessment tools. You can still apply all those after you've imported the CTFind3 results. Next step is particle sets. So let's say you have data from 1,000 different micrographs. I think in this project, we don't have quite 1,000. If I look here in the particles directory, so this little button I pressed over here, this image of a file folder, so the icons aren't terrific, opens up the E2 display program, which is a file browser and image viewer. If I look inside, for example, the particles directory, I'll see that there are quite a lot. Actually, let me go into the directory so it's easier to see. You can see there are actually quite a lot of micrographs here. Now, what we're seeing here is these are the particles from one micrograph. So this is the name of that particular micrograph. Then these are the CTF corrected version of the particles. And then these are the CTF corrected version of the particles after applying some additional filtration to make them suitable for some faster pre-processing, that sort of thing. But in a typical project, you may easily have hundreds or thousands of these images. This project looks like it has something on the order of about 500, I think, individual micrographs in it. So there's a question of how you deal with all of this data from different images. If you knew from the start that you were just going to want to process all of the data from all 500 images, then you could just merge all the data into one big file and have at it. But the practical reality is the data quality isn't the same across all of the images. You may want to work with only the best 10% of the data. You may want to work with the best 50% of the data. You may want to compare what you get when you work with the best fraction of the data with what you get from the worst fraction of the data. There are various things you might want to do. So we have this set concept, which allows you to basically reference particles in the existing particle files in text files, and then it will treat these text files as if they were actual image files. So I look in this particle sets directory. No, sorry. So there's a directory here called sets. And if I look in there, there's a bunch of files that have a .lst extension. These are the same file format that was used in EMAN1, if anyone there is familiar with EMAN1 at all. But these files will all look just like their image files. For example, this LST file has 85,000 particle images in it. But in reality, they're just small text files which contain references to other image files. This prevents you from having to have multiple copies of your data. So if I look at one of these text files, it doesn't matter which one, you'll see that basically it's just a list of particle number and file name for all of the different images that I want to reference. Now, the only trick to this file format, in a sense you could manipulate this as a text file, is that all of the lines in this file have exactly the same number of characters on it. And that number is documented up here at the top of the file. And that allows us to rapidly seek into a file. I mean, if we have 1 million lines in the file, we don't have to read one. We don't want to have to read 900,000 lines if we want to read the 900,001th particle. So this allows the fact that the lines are all the same length allows us to rapidly seek to different points within the file. But this mechanism allows you to generate many different subpopulations of your total particle population without having to replicate the data, and saves a lot of disk space and a lot of time when copying back and forth to the cluster. Yeah, so it ran, it just didn't pop to the front. All right. So once we've got our particle sets defined, then we can run reference-free class averages. And this is where the first place we'll see a reference to a Reliant compatibility. So you can use Eman's 2D class averaging process, or you can actually export your data and launch a Reliant refinement job as well. And once you've done one of these 2D refinements, then there's a tool which allows you to look at the class averages you got and, for example, find bad-looking class averages and then find the associated particles and eliminate them from future use in the processing. I'll go back and step through some of that stuff once I finish going through the overall procedure. Then the next step is making an initial model. For the most part, we just use this standard E2 initial model program that we've gotten here. But technically, you can use other software for doing that as well. Or if it's already, for example, say you're solving the structure of a ribosome, you're just trying to get the higher resolution, or you've modified it in some way or something like that, you could always just take an existing ribosome structure as a starting model and call it good enough. Generally speaking, your starting models do not have to be very good at all. In fact, my standard example is taking a structure of a cylindrical GrowEL molecule and refining it using an ellipsoid, just a featureless ellipsoid as a starting model. So your initial models don't generally have to be very, very good to produce nice final results. And it's almost always going to be obvious if you're getting an incorrect structure when you actually do the refinement. All right, so then we get to the meat of the matter. So this is Eman's refinement program, E2 Refine Easy. There's also E2 Refine Multi, which allows you to break data up into multiple groups if your particles have some amount of heterogeneity or motion, that sort of thing. So if you want to generate multiple three-dimensional structures from a single particle population, you can do that. Then you can also see the routines here for exporting your data into Reliant or FreeAlign for running 3D refinements there. Now, the question people often ask is, so I'm running with this graphical interface, and I'm running this on my local laptop here, and then you told me that I should run my actual refinement on the cluster. How? And then but you also told me I shouldn't use the GUI on the cluster. So how do I get my job started? So if we look carefully over here, we'll see when I pick a job, it asks me for a variety of parameters over here. I can fill in all the parameters. If I mouse over the parameters, it'll give me a little help documentation documentation telling me what the parameters are. There are tools for sort of filling in these values. The trick is, once you have filled in the values, there's another tab here which says command. And if I go to the command tab, it'll give me a command line which takes all of these arguments and embeds them into a command, and I can then copy and paste that command. So this is what you typically do. You'd go through all the earlier steps in the reconstruction process. Then you get to this refine easy task. You configure the refinement as you like it, and then copy and paste this into a script that you'd then submit to the batch queuing system on your cluster. So you'd rsync your project directory to the cluster. You'd create a batch PBS file or whatever, a job queuing file on the cluster with this command in it, including the parallel options which specify the MPI parameters and the number of threads that are available. Now I'll point out, when you're running in parallel, I sort of mentioned this a little earlier, there are two options that you may specify. There's a parallel option, and then there's a threads option. The parallel option is actually modular. Eman actually supports 3 different types of parallelism. MPI is one of them. Threaded parallelism is another. And a sort of novel distributed parallelism system is a third, which you probably don't normally want to run on a cluster. You'd normally run that on like several workstations you had in your lab if you didn't want to have to set up MPI. So generally, threaded parallelism and MPI are the two that you'd use most often. If you're running an MPI, as I mentioned before, there are a few tasks in the refinement process that it can't efficiently run on multiple nodes. It really needs to use shared memory to perform the tasks efficiently. So for those particular tasks, there's another option, which is threads, which tells it how many shared memory threads it can safely use within one node on the cluster. Okay, so normally when you specify this command, you'll specify both the MPI options here and threads here. Or if you're running on, say, a local workstation, which only has 16 cores and you're not going to be using MPI, you can say thread and the number of threads, and then you can fill in the same number of threads in the box over here, and it will use that. For a lot of tasks, for a lot of sort of intermediate or small scale projects, if you're basically just targeting slightly sub-nanometer resolution, you can probably do it on a decent sized workstation without having to even shift to a cluster. If you're going to target something very high resolution, something better than 5 angstroms, you'll almost certainly want to go to a cluster. Then once we finish the refinement process, we've got some validation tasks. We've got tilt validation available here. The gold standard refinement, which is also a sort of validation, already is embedded in the refinement process. There's a couple of options here for looking at resolution. So that's a quick overview of this workflow interface. Let me now show you some of the more general purpose widgets that are available in the system, primarily through this browser widget. Now again, I realize the font is probably a little bit small here and a little hard to read, so I'll try and identify things as I look at them. But basically, this is just sort of a standard file browser. It's just that it gives you some additional information like the size of the file, the dimensions of the images, the number of images in the file, for each file that you're looking at. So I'll go ahead and go into one of the refinement directories here. So inside the refinement directory, we'll see a whole bunch of image files, and these are intermediate files which are generated as part of the refinement process. Again, if you want to know details, descriptions of what all of these files are, if we go back to the wiki here, there is a page which documents what all of these files are. Header information. Oh, I think I moved it. Sorry. I think we put it output file descriptions and details. Here we go. So this will actually tell you what the meaning of all of those different numbered files that you find in a project directory are. So if we take any of these image files, and if I just single click on one of the files, for example, this is a file containing 2D class averages, I'll get a set of options at the bottom, which are context sensitive. So this is a stack of 2D images. So it allows me to show the images as a stack, and I can sort of zoom in and zoom out on the stack. The gray images are actually that. They don't have any good information in them. So I can see my stack of tiled images, or I could display them in a single image display, and then I could scroll through the images sequentially. You can see there's a lot of missing images here, but I can move back and forth between the various images. Now, all of the display widgets that are available in Eman follow a common convention, which is if you middle click on whatever the window is, it will pop up an associated control panel. So this is where I'd be able to do things like adjust brightness and contrast, gamma, that sort of thing. In the case of a tiled display widget, I can do things like mark specific images for deletion, and then I could save the file back to disk again without those particles, or I can rearrange the images. I can do a variety of different things. Now, the single image display has a few more capabilities that the tiled image display doesn't, which is one of the reasons why you're allowed to look at tiled images in the single image display. If I open up its control panel, you'll see I can do things like look at the Fourier transform, the power spectrum of the image. I can look at in fact, I can look at it in color, which shows me the phase information as well as the amplitude information. And then there's a variety of tools for doing things like measuring distances in the image, or for probing regions of density within the image and giving you statistical information about the area inside the box. A variety of different tasks. There's even a direct interface to Python here where you can type Python commands in the window and have it manipulate the image in various ways. So this is also a nice, useful, standardized widget. If we go to a three-dimensional volume, so this is one of the 3D reconstructions, you can see we get a different set of options. In addition to show stack and show 2D, so again, I could take my three-dimensional volume and I could look at it as a sequence of 2D slices through the volume, or I can open it up in a 3D display widget and rotate it around and do stuff to it. If I open the control panel for this, you can see again I get a completely different interface, and I can do things here like let's say I want to put a slice through my data instead of just looking at this isosurface rendering. I can just say add a slice, and now I have a nice slice going through the middle of my data. I could turn off the isosurface so I can see the slice. Then I could, for example, move the slice in space and move this, see what's going on in different directions. I could add another slice in a different orientation, and we could see how they intersect with each other. So there's all sorts of different things that you can do in this context. If I want to say rotate the slice, I can actually change my selection options there, and then I can rotate the slices independently and do various things. Now, this is not a bad visualization widget, and one of the things it allows you to do is display multiple volumes in the same widget. But we're not trying to replace other dedicated visualization tools like Chimera. This is just designed as a sort of a convenient tool for quickly looking at your data. So let's say, for example, I want to. I'll go ahead and open a new widget for this. I want to look at the refinement in this directory and compare it to the refinement in another directory. So I can double click on this, and that'll use the default. Oh, sorry. That'll open it up in the same widget by default. I'll use the plus button here, which will open a new window for it. Then I'll go to a different folder, and I'll take one of the 3D refinements from that folder. And this one was higher resolution. This was just sort of a test project for me, where I was playing with different refinement options and that sort of thing. So now what we have in this window are two overlaid structures. Okay, one is a little lower resolution, one a little higher resolution. What we can do now in this control panel is we have this slider down here, which allows me to switch between the two models. And this is a very nice way of comparing one model to another visually. If I zoom in here, for example, this is a nice alpha helix here and another alpha helix here. I can see that in the higher resolution version, I can see that a lot of the side chain information now sticking out from some of these alpha helices, whereas in the low resolution version, a lot of that stuff was filtered out. So there are a lot of really interesting things you can do with this tool. If you want to go to a full featured visualization package, there's a nice Chimera button, which will just allow you to immediately open the image object in Chimera and use all of its visualization capabilities. One other thing I haven't shown you, and this works both for 2D and 3D, is this filter tool program. And I guess I'll probably stop with that. I mean, we've only sort of touched on the highlights of the system, but we'll probably stop after this. So if I launch this filter tool application, it will open a window containing whatever image I'm interested in, image volume, whatever it is. And let me play with the isosurface threshold a little bit. And we'll zoom in a little so we can see it. So again, this is a fairly high resolution map. Let's say I want to do something to the map. Oh, that's interesting. I realized that didn't work. All right. So the window that I've gotten here allows me to build a chain of image processing operations. It opened up with a default chain, which is the last set of operations that I did when I was in this particular project directory. So what this gives me is access to all the different categories of image processing operations that are available in the system. So we have transformations, we have normalization operations, mathematical operations, filters, masks, all sorts of different things. So what I'll do here is I want to do a low-pass filter. So I'll select filter first, and then here I'll see a list of all of the available filters. So here, for example, is a low-pass Gaussian filter. And that'll give me a list of options specific to that filter. If I mouse over, it'll give me help and tell me what that option means. So this is the resolution of the filter. Now, when I initially create this filter, it's turned off. This little checkbox here enables or disables the filter because some operations you perform might take a long time to run. It allows you to set the parameters first and then turn it on just in case it's one of those. In this case, it shouldn't be too slow. So I'll go ahead and check the checkbox here. And now we'll see, oh, look, at low pass filtered, but all of my density vanished. That's because the isosurface threshold also changed when I did that low pass filter. So there's a low pass filtered version of my map, and I can interactively drag these sliders, and it's a pretty big volume, so it's not super fast, but I can interactively play with the different values. Instead of dragging the slider, I could type a value directly in the box too, and filter it to a desired level. And then I could add another filter. Let's say I wanted to mask out some portion of the density. I don't know why, but let's say I wanted to do a spherical mask. Let's see, mask dot, here we'll do a soft spherical mask. And then this process allows me to define a center for the mask, inner radius, outer radius, etc. So we'll set an outer radius of, say, I don't know, 50 pixels. And then I'll turn the mask on, and we should see, yes, now we have just an inner sphere of density representing our particle. If I want to rearrange the order of these operations, say I want the sphere to go first, I hit this arrow, and that'll put the mask before the filter. And once that's been done, let me turn it on and off again just to make sure it's happening. Yeah, once that's been done, now you'll see that the edge of my sphere has become soft because the edge is getting filtered as well. I could also have done that by making the mask softer, but yeah, it's just a slightly different methodology. And one of the nice things about this tool is once you've put together one of these chains of filters, if I exit all of these graphical tools, I'll find that in my project folder, there's a file now called filter tool. It's called default because that was the name of the filter chain that I built, which contains options which I could use with other programs like E2Proc2D or E2Proc3D to process a bunch of different data sets using that same set of filters that I defined using one particular sample data set. Okay, we've gone for an hour now, so I think I'll go ahead and stop with the presentation at this point. If anyone has any last questions out loud or otherwise, please feel free to ask them. Otherwise, we'll just sort of wrap it up. If you want more information, I encourage you to go to the wiki, work your way through one of the tutorials, and it'll teach you a lot of the features of the system.
Great, yeah. And if anyone has any questions, feel free to put them in the chat. I'll pass them on. Thank you very much, Steve. EMAN2 is very impressive. Thank you particularly for the command tab. I would like to urge you to talk to all other software developers and urge them to add the command tab to all of it.
Yeah, that was added for a reason.
Well, great. I think we'll wrap up with that. Thank you again, and I'll follow up with you offline.
Okay, sounds good.
Great. Bye.
Bye.